Hello students. So in this session we are going to see the continuity of composition function and then few more different types of problems we will discuss. Okay. So continuity of composition of functions. Continuity of composition of functions. Suppose f and g are any two real valued functions and f composition g is defined at C, f composition g is defined at C and g is continuous at x equal to C and f is continuous at g of C. Okay, then we say that the function f composition g is continuous at x equal to C. What is it? The statement, how we can write the definition? F and g are any two real valued functions or real function, okay, real valued functions, and f composition g is defined at x equal to C. We say f composition g is continuous at x equal to C if g of x is continuous at x equal to C and fx is continuous at g of C. So this is the definition of continuity of the composition of functions. If f and g are any two real valued functions and f composition g is defined at C, we say f composition g is continuous at x equal to C if g of x is continuous at C. The middle one here, the first, this g is continuous at C and f is continuous at g of C, right? So because f composition g of x, how we write? We write like f of g of x, right? So that's why the inner function, it should be continuous at C first. Then f is continuous at g of C. We say f composition g is continuous at x equal to C. We see some example for this. So we take a function, show that the function fx is equal to sine of x square is a continuous function. Okay, so work on this. Fx is equal to sine of x square. You know, when x is real, x square is also real, right? When x is real, x square is real. When x square is real, then definitely sine is defined for all real values, right? Are you understanding the logic? When x is real, x square is real. When x square is real, then sine is defined for all the real values. So its domain is R. Clearly, domain of f is R. Okay, domain of f is R. Next, what I do is I'll take it as this function as composition of two functions. That means I'll take h of x is equal to, let g of x is equal to sin x, and h of x is equal to x square, I take it. Okay, g of x is sin x and h of x is x square. If I take this one, g composition h of x, g composition h of x, that means g of h of x. What I am getting? G of h of x is x square. So g of x square is going to be sin of x square, right, which is same as fx or not. So that means we have taken fx as composition of two functions g and h. Now you observe h of x is a polynomial, right, of second degree. It's a polynomial function, we can take it. H of x is equal to x square. So this is definitely continuous throughout the real number system, because we proved every polynomial is continuous. That means it's continuous at each and every real number. That means h of x is continuous throughout the real number system. Okay. Then when h of x is continuous throughout the real number system, then definitely sin of x square, even sin x is also continuous throughout the real number system. We proved, polynomial is continuous and sin x is continuous. Both were continuous throughout the real number system. Therefore, the composition of these two functions is also continuous. Right? You just recall 2 points here. One is the polynomial function is continuous, right? In throughout the real number system it is continuous because it's quadratic, right? And we proved sin x is also continuous function in throughout the real number system. That means h of x is continuous throughout the real number system. So its composition sin of x square is also continuous. How we write now? It is clear that h of x is equal to x square is continuous on R, and g of x is equal to sin x is also continuous on R. Okay. Now the composition g composition h of x, which is equal to sin of x square is continuous on R, because x square is continuous at each and every real number, right? When x is real, x square is also real, so sin is also continuous throughout the real number system. So therefore, the composition is also continuous, which is equal to fx is continuous on R. Okay, right? So in this way we can tell that, because both were continuous functions. X square is continuous at each and every real number, and this g of x is continuous at each h of c. That's why g composition h of x is continuous. Still, if you want to write elaborately, you can write in another way, like h of x is equal to x square is continuous for all c belongs to R. Okay, and sin of x square, okay, is continuous for all h of c belongs to R. Okay, so sin of x square is sin x is continuous for all h of c belongs to R. So final conclusion, what you can write? So sin of h of x is continuous for all C belongs to R. It means h of x is x square. Sin x square is continuous. Okay, if you want to write still elaborately, you can write like that. Okay, h of x is equal to x square is continuous for all C belongs to R, and sin x is continuous for all h of C, okay, which is also belongs to R. H of C means C square, and so sin h of x is continuous for all C belongs to R. Therefore, sin x square is continuous. Right, we will discuss one more problem. The function f defined by, show that the function f defined by fx is equal to mod 1 minus x plus mod x is continuous. Is continuous. Yes, we can prove again the same way. It is clear that it is defined throughout the real number system. Okay, fx is defined on R. Okay, we take let fx is equal to, let g of x is equal to mod x and h of x is equal to 1 minus x plus mod x, 1 minus x plus mod x. Here this h of x is a sum of two continuous functions. Sum of two continuous functions. This is a linear polynomial, this is a modulus function. We proved mod x is continuous. We proved polynomials are continuous. So sum of two continuous functions is again continuous. Okay, as mod x comma 1 minus x are continuous on R, mod x plus 1 minus x is also continuous on R. Okay, right, h of x is continuous on R, we got it. That is h of x is equal to 1 minus x plus mod x is continuous. So when x is or something, if you take c, for some value c, if you take it real number, then h of c, what do you get? 1 minus c plus mod c. It is again another real number, right? Let c belongs to R if we take it. Then what will be h of c? You get 1 minus c plus mod c. It's again a real number, it is also a real number. When c is real, then 1 minus c plus mod c is also a real number. Now I can say that g of x is continuous at h of c, because h of c is a real number, it is. Since h of c is a real number, then therefore g of x is equal to mod x is continuous at h of c. Okay, at h of c, definitely, because h of c is a real number, it is. So that means that is g of x, that is g of h of x is equal to modulus of 1 minus x plus mod x. Okay, is continuous on R. Okay, so finally we will write hence fx is equal to mod 1 minus x plus mod x is continuous. Okay, like this way we can write it. Okay, this is a continuity of composition of functions. Just these two problems, you can work it out in the textbook also. You may have some 2 more problems are there, you can work it out those. Now we will see some more important problems which came in the PU board examination also. Find all the points of discontinuity. Find all the points of discontinuity of the function fx is equal to mod x by x if x not equal 0, 0 if x equal to 0. Mod x by x if x not equal to 0, 0 if x equal to 0. You know, you are aware of this function. What we call it is a Signum function or sine function, which we have studied in first PUC. Okay, in special functions we have studied this one. Signum function we call it is. Okay, we will see fx is equal to given fx is equal to mod x by x if x not equal to 0, 0 if x equal to 0. That means it is very clear the function is defined throughout the real number system, right. X not equal to 0 means it may be either less than 0 or more than 0. 2 cases are there. X not equal to 0 means either x is less than 0 or x is more than 0. So we will split this x by x if x greater than 0, and we will write 0 if x equals 0, whatever they given, and if x is less than 0, when x is less than 0, mod x become minus x by x. So that means we get like this: 1 if x is greater than 0, 0 if x equals 0, minus 1 if x is less than 0, right. So this is the function they have given it to us. Fx is equal to 1 if x greater than 0, 0 if x is equal to 0, minus 1 if x is less than 0. That means the function is clearly splitting at 0. The function is clearly splitting at 0. That means less than 0 one function, more than 0 the function is defined as 1, and if x equals 0 they have given the value as 0. So that means the function is okay, keep on changing for less than 0, for more than 0, equal to 0 here. Now we work it out in 3 cases. What are those 3 cases? C less than 0, C equal to 0, C greater than 0. 3 cases we have to work it out for this problem. Okay, and what is the doubting point? The doubting point is x equal to 0. Okay, why we call it as a doubting point? Because the function is splitting at x equal to 0. That's the reason. Okay, now we'll see. First we write clearly fx is defined on R. So domain of f is R. So we have to write compulsory because we are discussing continuity on its domain. That's the reason we always write what is its domain first. Now, case 1. Case 1. Let C less than 0 be any real number. Be any real number. Okay. Then f of C. Then f of C is equal to what? For all c less than 0, for all x less than 0, the function is minus 1 they have given, right. So that's why f of c is going to be minus 1 now for all negative values, right. F of c is minus 1. Now whether it is required left hand and right hand limits? No, not required, because for all less than 0 the function defined as minus 1. That's why we won't work it out left hand and right hand limits here. Okay. Now limit x tends to c fx, which is equal to limit x tends to c limit x tends to c, fx is what now here? It is minus 1. So, limit of a constant is constant minus 1, right. Now, what we can write, therefore, limit x tends to c, fx is equal to f of c, because the limiting value is same as functional value, okay. Limit x tends to c, fx is equal to f of c. It is true for all c less than 0, okay. So, fx is continuous for all, okay, x less than 0. Next, case 2 is always important for us because it is splitting, the function is splitting at 0, okay. So, at x equal to 0 will work it out. You can take c is equal to 0 or x equal to 0, no problem, okay, but don't confuse. At x equal to 0, then what is the f of 0 they have given? F of 0, they have given the value 0 here. Now, we work it out, limiting value. So, now is it necessary the left hand and right hand limits? Yes, because the function is splitting at 0. So, we need to work it out, left hand limit and right hand limit. Now, LHL, limit x tends to 0 minus fx. So, limit x tends to 0 minus, that means approaching to 0 from left, that means x less than 0, function is minus 1. So, limit of a constant is constant minus 1, and RHL, limit x tends to 0 plus fx. So, limit x tends to 0 plus, that means approaching to 0 from right side. So, that means the value, x value will be more than 0. So, you have to take the function as 1 is equal to 1 this is. It is very clear, left hand limit is not same as right hand limit. Left hand limit you are getting minus 1 and right hand limit you are getting plus 1 in this place. Okay. So, limit x tends to 0 minus fx is not same as limit x tends to 0 plus fx. Therefore, limit x tends to 0, fx does not exist. So, limit itself is not existing, then we can't go for continuity, right. So, we will conclude that. So, fx is not continuous at x equal to 0, because we are working at a particular point, no, that is why I prefer to take x equal to 0, okay. You want to take c is equal to 0, no problem, c is equal to 0 you can take it, okay. Then f of c will be 0, you are right. Limit here x tends to c minus, c plus, like that, because when you are working at a particular point, better always to take x only, okay. Right, case 3. Let c, we worked out for less than 0, we will work it out for more than 0. Let c greater than 0 be any real number, then by the definition of the function f of c, it become 1 it is, because for all positive values they have given the functional value as 1, they have defined it as 1 now. Now, whether it is required left hand and right hand limits, not required, because we are working only for more than 0. For more than 0, only the function is defined as only a single, right. That means it is not changing, it is a single function like for all positive values, right. F of c is equal to 1 now. Now, limit x tends to c fx. So, limit x tends to c, okay. So, for all positive values the function is defined as 1 it is. So, you are getting 1 in this place because limit of a constant is constant. Therefore, limit extends to C, fx, limit extends to C, fx is equal to f of C. It is true for all C greater than 0. That means, so fx is continuous, for all x greater than 0. Now, by case 1, case 2 and case 3, what we can conclude now? This function is continuous throughout the real number system except at 0. Right? It is continuous throughout the real number system except at 0 because at 0 it is not continuous, we proved in case 2. Right? So, by case 1, case 2, case 3, by case 1, case 2 and case 3, okay, by case 1, case 2 and case 3, what we conclude, the only point of discontinuity of fx is x equal to 0. This is the only point of discontinuity for this function, right? So, this is about Signum function. Are you clear? Right? So, it is also one important model. 3 cases problems are important for us for the examination point of view. Right? Next, we will go for another problem. Okay, we will see one more problem. Find the relationship between A and B. Find the relationship between A and B so that the function f defined by fx is equal to ax plus 1 if x less than or equal to 3, bx plus 3 if x more than 3. If x is more than 3, is continuous at x equal to 3. Is continuous at x equal to 3. Now, they are already given here in this problem, the function is continuous at 3. When we say that the function is continuous at x equal to 3, the left hand limit of the function at 3 is equal to the right hand limit of the function at x equal to 3 is equal to the functional value at x equal to 3. All the 3 are going to be equal here because they given it is continuous. Now, see that solution. Given fx is equal to ax plus 1 if x is less than or equal to 3, bx plus 3 if x is more than 3. They have defined like this. Given fx is given fx is continuous at x equal to 3, which implies the left hand limit, that means limit extends to 3 minus fx is equal to right hand limit extends to 3 plus fx is equal to f of 3. So, the left hand limit at 3 must be equal to the right hand limit of the function at 3 is equal to the function value at 3. Now, limit extends to 3 minus means x is approaching to 3 from left, x is approaching to 3 from left, that means the function is defined as ax plus 1. So, we will write it as like this, ax plus 1. Limit extends to 3 plus, that means x is approaching to 3 from right side, that means the values are more than 3. Then you have to take the function bx plus 3 is equal to f of 3. F of 3 means here in this place equal to 3, they define it as ax plus 1. That means you get 3a plus 1 because f of 3 value is equal to 3, they define like this. So f of 3 become what? A into 3 plus 1. That means 3a plus 1. Okay. Now limit extends to 3ax plus 1 become what? It's a linear polynomial, right? So whenever you are working for polynomial, you just right away substitute it, okay, without any doubt. So a into 3 plus 1 is equal to, here also it's a linear polynomial. So b into 3 plus 3 is equal to 3a plus 1. So what we are getting? 3a plus 1 is equal to 3b plus 3 is equal to 3a plus 1. Right? 3a plus 1, it is both were same, one time you write it. So which implies 3a plus 1 is equal to 3b plus 3. Now take that 3b to this side and 1 to the other side. 3a minus 3b is equal to 3 minus 1. 3a minus 3b is equal to 3 minus 1 means 2 it is. So 3 if you take common, 3 times of a minus b is equal to 2. Therefore, a minus b is equal to 2 by 3. Okay. This is the relation between the a and b when the function is continuous at x equal to 3. This is the required relation. Okay. So we will go for another problem. Determine the value of k. Determine the value of k if fx is equal to k cos x divided by pi minus 2x if x not equal to pi by 2. If x not equal to pi by 2, 3 if x equal to pi by 2 is continuous at x equal to pi by 2 is continuous at x equal to pi by 2. Now you need to find out the value of k so that the function is continuous at x equal to pi by 2. So we take the given function fx is equal to, always better to write one time the given function as it is, k cos x by pi minus 2x if x not equal to pi by 2, 3 if x equal to pi by 2. This is the function they have given it to us. And now if f is continuous at x equal to pi by 2, then we need to find out k value. Let we take it here. Fx is given, fx is continuous, given fx is continuous at x equal to pi by 2. Then what we can write? Left hand limit at pi by 2 of the function and right hand limit at pi by 2 of the function must be same as the function value at pi by 2. Now we will write the functions here. Limit extends to pi by 2 minus means here x not equal to pi by 2 they have given. That means when x is less than pi by 2 or x is more than pi by 2, it is the same thing. That means you can work it out a single limit here. You don't need to work it out left hand and right hand limits in this place. Why? Because the function is same when x is coming close to pi by 2 either from the left or from the right. X not equal to pi by 2 meaning is either x is less than pi by 2 or x is more than pi by 2. So, limit x tends to pi by 2, fx must be same as f of pi by 2. Okay. We don't need to work it out left hand and right hand limits here. Next, limit x tends to pi by 2, fx is k cos x divided by pi minus 2x, which is given as f of pi by 2 value is 3 this is. Now, what we can do is here k is a constant, you just write outside k into limit x tends to pi by 2, limit x tends to pi by 2 cos x divided by pi minus 2x, which is equal to 3 it is. K into here this cos x we write it as sin pi by 2 minus x, sin pi by 2 minus x we write it, limit x tends to pi by 2 sin pi by 2 minus x divided by, from this we take 2 common, from the denominator here. Okay. So, when you take 2 common, then you get pi by 2 minus x, because it is a pi minus 2x, no, you will get pi by 2 minus x. See that when you multiply this 2 to get cancels, pi you are getting minus 2 into x, pi minus 2x, it will be balanced, is equal to 3. So, k into when x is coming close to pi by 2, okay, then x minus pi by 2 or pi by 2 minus x come close to 0. Okay. So, as x is coming close to pi by 2 and x is come close to pi by 2, then definitely pi by 2 minus x goes to 0. So, pi by 2 minus x goes to 0, sin pi by 2 minus x divided by pi by 2 minus x, here 2 is present in the denominator, I will write outside the limit k by 2, which is equal to 3, and it is a known formula to you, right? Limit theta tends to 0 sin theta by theta, the value is 1. Okay. Because of this, what I can write this entire value, limit theta tends to 0 sin theta by theta, this value become 1 is equal to 3 this is. Therefore, or which implies k by 2 is equal to 3, therefore k is equal to 6. This is the value of k. K value is 6, we got it. It's one of the very important problem. It's keep on repeating in the PU board examinations. Okay, one of the important model this is. K is equal to 6. And then finally one more problem we do it and we end this session. Discuss the continuity of the function, discuss the continuity of the function fx is equal to x square sin 1 by x if x not equal to 0, x square sin 1 by x if x not equal to 0, 0 if x equal to 0, 0 if x equal to 0, at x equal to 0. Discuss the continuity of the function at x equal to 0. This is the question. At 0 we need to work it out. Okay. So, this is the given function. The given when x equals 0, the function value is 0 they given. That means f of 0 is 0 from this. Solution, given function, given fx is equal to x square sin 1 by x if x not equal to 0, 0 if x equal to 0. So, we are working at 0 now. F of 0 is equal to 0 it is. At x equals 0 we are working. Okay. F of 0 is 0. Then limiting value, is it necessary the left hand and right hand limits at 0? No, not required, because x not equal to 0 meaning is either x is less than 0 or x is more than 0, right. That means when x is coming close to 0, when x is coming close to 0 either from right or left, okay, the function is the same thing it is, right, because x not equal to 0 meaning is either x is less than 0 or x is more than 0. X not equal to 0 means either less than 0 or more than 0. So that's why you don't need to work it out left hand and right hand limits, you work it out limit x tends to 0. Now limit x tends to 0, fx we consider. So limit x tends to 0, x square into sine 1 by x. Limit x tends to 0, x square sine 1 by x. When x is tending to 0, what about 1 by x? What about 1 by x value? Okay. So you all know that graph of y is equal to 1 by x. Okay. It will be like this, right? It will be like this, the graph of 1 by x. That means when x is coming close to 0, what happens? The 1 by x value either goes to plus infinity or it goes to minus infinity. When x is coming close to 0, from right side it goes to plus infinity. When x is coming close to 0, from the left at the time the y value goes to minus infinity. That means what we can write here, 0 square into sine of 1 by x, sine of 1 by x. What I can write in this place? It's any real value between minus infinity to plus infinity. It's going sine, just infinity will write. Okay. Whatever maybe it is, inside of sine. Okay. Whatever the value, it may be plus infinity or minus infinity, whatever it is. But sine always gives values between minus 1 and plus 1, because sine is a bounded function. Bounded function means we all know that range of sine x. Okay, range of sine x is minus 1 to plus 1. Sine is defined throughout the real number system and sine lies between minus 1 to plus 1. You have to understand this point. Sine is a bounded function, that means it's having some bounds. That means minimum value is there, maximum value is there. Minimum of sin x is minus 1 and maximum of sin x is plus 1. So what I write now in this place, 0 square is 0 into, I will write just a finite value between minus 1 and plus 1. A finite value between minus 1 and plus 1. So 0 into a finite value is going to be 0 we get, right. So if you want to solve this, you must know the idea on 1 by x and as well as sin x. Sin is a bounded function, okay. It always lies between, the values always lies between minus 1 and plus 1, okay. So 0 into a finite value we are getting 0. That means limiting value we got 0 now. So limit x tends to 0, x square sin 1 by x is 0, which is same as f of 0. That means the limiting value of the function is same as the functional value. Therefore, what I can conclude now, therefore fx is continuous, fx is continuous at x equal to 0. Okay. So I hope you understand. So you must have little idea on sine, domain and its range, and as well as the 1 by x graph. Okay, right? This is one of the important model. Here many of the students will do mistake in this place. Okay, right? So with this the concept of continuity is completed, and then in the next session we are going with differentiability. Okay, thank you.